we continue the interpretation of International Tables page. So, this is part 3 of the series, and in this video we will discuss general positions diagram. So, this is the space group which we have been focusing on, that is space group number 66, and in the previous two videos of this series we first discussed the headline. So, the details given here, and then in the next one we discussed what is called, there are two kinds of diagrams given here. One is the diagram which is diagram of symmetry elements, symmetry element diagram, and the other one, this last one here, is general position diagram. Of course, in this space group there are two more symmetry element diagrams which are different projections as we have seen. So, in the current video we will focus on the general position diagram. So, this is a magnified view of the general position diagram. You can see in at one glance it looks a complicated diagram with several circles and commas and plus and minus signs and fractions, half plus and half minus. So, what we will do is to build this diagram one by one, so as to gain a better understanding. So, I start with an empty unit cell here, the projection of an empty unit cell, and I have the same projection AB projection. So, this is the A direction and this is the B direction, this is the origin O, and we start with what is called a general position. So, what really is meant by a general position, that a position which is not lying on any symmetry element. So, a general position is a position which does not lie on a mirror plane, does not lie on a rotation axis, does not lie on an inversion point, and it does not lie on any specific symmetry element. So, the site symmetry, the symmetry at which the point is located, is the identity. So, that is what is called a general position. So, that is why I have selected a location like this, because you can see from the symmetry diagram which we had, you can see the symmetry diagram here. So, I mean to select positions. I am not showing all the symmetry elements there, but you can think of that my circle is somewhere here with respect to the symmetry diagram. So, that is why it is not lying on any symmetry element. Then, so that is the starting general position. After that, we have to apply symmetry elements one by one to generate other positions which are symmetry equivalent. So, recall that one of the symmetry elements of this diagram here shown here is a mirror plane parallel to or along the projection plane. So, this is shown by this two lines at 90 degrees to each other. So, there is a mirror plane, and we also give a height. See, if this circle, if the blue circle is exactly on the projection plane and projection plane is a mirror plane, then obviously this is not a general position. So, we will have to lift this point up from the projection. So, to lift it up, I give a symbol plus to it. I give a symbol plus to it. Plus here stands for actually plus z, means its z coordinate is some arbitrary value of z, but it is above the xy plane, it is above the AB plane, and its height above the AB plane is z. But to keep the diagram simple, z is not required and only plus sign is given, which means that it has some coordinate above the some height above the xy plane. Then now let me apply this mirror symmetry to it. As soon as I apply the mirror symmetry, you can see this from a 3D visualization. So, this is my mirror plane, the projection plane, and if this is my general position here, and its height above the mirror plane is z. So, I am writing it as plus, but then if I reflect it, it will go below the mirror plane and will also change the handedness, and changed handedness in the crystallographic notation is shown by a comma. So, I represent it by a comma and below this plane. Now, if it was above a height z above the mirror plane, then it will exactly again be a height z below the mirror plane, the image point. If I project these two, they will project in the same location. So, in the projection, one has to represent 2 points, one above at plus and another below at minus z, and the two are of different handedness. So, the standard notation used for this is to divide the circle into half. My division is not very, divide the location into half, and then look at the show the change in handedness by comma in half of the circle. So, these two circles are representing now these 2 points as shown in the 3D perspective on the right, and instead of plus z, now this is at minus z, which I simply denote by minus. So, I get two positions, two equivalent positions related by mirror at this location. Let us look at consult the symmetry diagram. Another important symmetry is this two-fold axis with a center of inversion. This two-fold axis is perpendicular to the mirror plane, and so in my perspective diagram, that will be a two-fold axis perpendicular to the mirror plane, and in the projection notation it is shown like this, and a center of inversion is also, if you see the symmetry diagram, a center of inversion is also shown by a hole in this lens. So, I create a hole. Of course, you know that this particular site symmetry will be considered as 2 by m, because there is a two-fold axis and there is a perpendicular mirror plane, and you know that whenever you have a symmetry like 2 by m, the intersection point develops as a center of inversion. So, that is what is being represented there. So, now if what will happen if these two equivalent points which are there, if I apply this two-fold axis at the origin, two-fold rotation about an axis passing through the origin. If I do that, then I will develop both of these points will rotate by 180 degree. So, in the projection plane they will go like that. So, you can see here in the 3D drawing, if I draw, so it is rotated by 180 degree to that location, and then its projection also will, its mirror reflection will go that way. So, again in this new location you will have both the handedness objects, and the height does not change due to the two-fold rotation perpendicular to the mirror. So, plus will remain plus, minus will remain minus, and left-handed will remain left-handed, and right-handed will remain right-handed. So, we will get another two equivalent positions there. The center of inversion is automatically satisfied, because you can see the plus here will be inverted to minus below. So, plus above will be inverted by the inversion center to the minus side and will change handedness due to inversion. Now, so I have four equivalent positions now which satisfy the mirror and the twofold, but you can see there are many other equivalent positions here. So, how are they getting generated? So, let us look at consult the symmetry diagram. In the symmetry diagram we find that one of the symmetry which we have not yet considered is this glide operation. This dotted line is representing a glide operation, and the glide vector, since it is dotted, the glide vector is into the plane of the paper or out of the plane of the paper. It is perpendicular to the plane of the paper. So, it is a C glide, and the C glide, the glide vector will be C by 2. The glide vector will be C by 2, which in crystallographic notation, in fractional coordinate notation, we will simply represent by half. So, which means there is a mirror plane there. I will reflect the object into the mirror plane and then translate by C by 2 perpendicular to the plane. So, it will go there and will translate up by half. So, let us do it in the diagram here. So, this plane, first let me try to make this, give this the symbol of glide, C glide. So, C glide by this dotted lines. So, I reflect it, reflection takes it there, reflection will change the handedness. So, the right handed will become left handed and left handed will become right handed. And you can see that if something is at Z and I translate it further C by 2, so it will go from Z to Z plus half, or we can write it as half plus Z. So, just like for plus Z we use the shortcut of writing only plus. So, similarly for half plus Z we will use the shortcut of writing just half plus. Similarly, the minus 1 will also reflect. On reflection the height does not change, it remains at minus Z, but then when we translate by C by 2, that is half. So, it will become half minus Z, which will be represented simply by writing half minus. So, I now have 6 symmetry equivalent positions. All symmetry operations act on all points. So, now the twofold axis which I am showing and at the center will act on this newly generated set of equivalent position. So, it will simply rotate it by 180 degree to reach there. So, I can then add 2 more points at 180 degree away without change of handedness and without change of height. So, half plus will remain half plus, half minus will remain half minus. Let me lower this diagram so as not to clutter there. Okay. But there are still more symmetry elements. Have we satisfied all of them? So, you can see that there is a glide here also. So, what will happen if I apply that glide? You can see that we have already applied that glide because these two positions are related by glide. You can see plus, which was without comma, on reflection will go to half plus and will change the handedness. So, we will have the comma. So, this other glide is an automatic result of the operations which we have already followed, but since it is present in the crystal, it is shown there. Similarly, you can convince yourself that this 1/4 twofold is already used in creation of these these 8 positions. So, in the end these 8 positions satisfy all the symmetry elements in and around that lattice point. So, we have created now this motif, but there are many other equivalent positions shown in this diagram, in the symmetry diagram. Those will get generated now simply by translations, because remember that this is a C centered lattice. So, first of all lattice points are at each corner of the unit cell. So, identical motifs will be placed at each lattice point. And since it is C centered lattice, so the center of the base is also a lattice point. So, again an identical motif is placed at that center of the base. So, then this completes the entire general position diagram. If you count the number of general positions within the unit cell, so you can see that there are 16 general positions within the unit cell. So, I will be counting 2 here, 2, 4, 6 and 8, and there will be 8 in the center. So, there are 16. I am not counting for example these, because these are outside the unit cell. So, within the unit cell there are 16 positions. So, the number of positions within the unit cell, number of equivalent within the unit cell is called multiplicity of the position. So, this is the general case. In this special case, we see that the multiplicity is 16. So, that completes the discussion of general position diagram. Thank you very much.